Welcome to this workshop organised by Engineers Without Borders UK and Hydrogeologists Without Borders UK. Well, first of all, let me thank Engineers Without Borders UK Birmingham branch for organising this room, organising the promotion of this workshop, and also for the filming of this workshop. So, and a special thank you to Agota for organising all this, so thank you. This workshop is designed to introduce to you the competition entitled Before the Well Runs Dry. This is a competition challenging engineers and young innovators to come up with a new design of technology to monitor water levels within boreholes and wells. We hope that through this workshop we can sort of introduce to you the problems, well, first of all, introduce to you why it's important to monitor groundwater levels, and then secondly sort of introduce to you the problems associated with monitoring water levels at the moment, introduce to you some of the technologies that are being used at the moment to monitor water levels, and then finally tell you what the point of this competition is, what we're hoping to achieve through this competition, and what kind of technology we're hoping to see at the end of it. So we've got two fantastic speakers here today. We've got Professor Richard Carter, who is a world-renowned guru in water management and development. In his career so far, he's been the, you'll have to correct me if I get any of this wrong, the Professor of International Water Development at Cranfield University, the head of the Technical Support Unit at WaterAid, the editor of the journal Waterlines, and the chair of the Rural Water Supply Network. We've also got Peter Dumble, who is a hydrogeologist with over 35 years of experience and was the creator and managing director of a Birmingham born and bred company called Waterra, which was one of the lead suppliers for groundwater monitoring equipment in the UK. And I say was because it's now Waterra in situ. So it's changed name. This is the workshop overview. Richard's going to kick us off with a description about why it is important to monitor groundwater levels, and talk a little bit about why there's such a scarcity of water data being collected from developing regions. Peter will then give an overview of the current monitoring equipment which is on the market at the moment, and then Richard will describe the sort of challenges that any new type of technology will need to overcome to, I suppose, surpass existing monitoring equipment. And then I will finally give a quick outline of the competition structure. And then right at the end we'll have a question and answer session. So for those of you who are watching this on your computer, welcome to Birmingham University. Press pause, go and make yourself a cup of tea and relax and enjoy the next 45 minutes.
Well, thank you very much, Geraint, and welcome everybody, whether online or in person. I'm going to be quite brief in this talk and the short one that I'll give after Peter has talked about some of the existing equipment. But in this first short presentation, I've been asked to say, well, it's a bit of a long title, but why groundwater monitoring is important, and why groundwater level data is collected only in limited volume at the moment. I'll just give a few thoughts on that. Water resources are really unlike almost any other resource other than the weather itself. They vary, water resources vary in quantity and quality over very short and very long time scales, and very short and very long distances. Water's constantly moving, it's a very dynamic resource. And people have realised this for a very long time. If you look back to Heraclitus, the Greek philosopher, he had a little phrase called panta rei, which means everything moves, everything flows. And one of the things he said is everything changes, nothing remains still, and you cannot step twice into the same stream. It's a very nice saying to sum up the dynamic nature of water. It's very routine to monitor weather, to measure and monitor river flows, stream flows, although in low-income countries, developing countries, even both of those activities are commonly under-resourced. But when it comes to groundwater is very often out of sight and therefore out of mind. And it tends to be very poorly understood. We still find people talking about underground reservoirs, underground seas, as it were, and people sort of conceptualizing groundwater as though it's an infinite reservoir of water that we can just take for as long as we want. And of course you know that nothing is further from the truth. And all of that is really despite the heavy dependence in many developing countries, in sub-Saharan Africa, in South Asia, on groundwater. Probably 50 to 70% of the populations in those developing countries depend in some way on groundwater. And that may be through boreholes from which water is abstracted by hand pumps or motorized pumps. Furthermore, in many developing countries, we're dealing with very extreme levels of seasonality and variability from year to year. So what we can see in groundwater levels is very steep declines in the dry season, and sometimes runs of dry years when groundwater levels just continue to fall before there's some replenishment of groundwater, some recharge of groundwater, which then allows those levels to recover. And there are some, I think it would be true to say generally that groundwater recharge in dry zones tends to be very episodic. It doesn't occur every year. It may only occur 1 year in 10, but it can be enough to provide an adequate resource. When Tanzania's business capital was moved from the coast inland into a dry region in the centre of the country, the city of Dodoma, not really very much thought was given to where the city would get its water. Where it does get its water is from a major aquifer, which seems to be too good to be true. It has continued to supply water to a growing city, but it can only do this because it gets infrequent but large amounts of recharge, which allow the levels to recover maybe every 5 years, 10 years, 15 years. And in between, it gets no recharge at all. And thinking about water and water balances, I always make the analogy between a water balance and a bank balance. You wouldn't go drawing down your bank account month after month after month without checking on what's going in and what the bank balance actually is. And it should be exactly the same with groundwater, that we should be keeping track of what's there. Measuring water levels, groundwater levels, at intervals of anything from a few seconds to a few weeks or longer can be extremely informative. And in Peter's talk, he'll show you just a little bit of data which illustrates some of the kind of conclusions that we might be able to draw from monitoring data. I think if there is one single routine measurement relating to groundwater resources, which ought to be taken regularly and on a much more widespread basis. It is groundwater level data. How do groundwater levels change over time, and what's the spatial distribution of groundwater levels? And that's why this competition has been put together. There are many constraints to implementing good groundwater monitoring, but one of those constraints may well be the non-availability of suitable equipment which is cheap enough to mass produce and accurate enough to inform water managers, and as well simple enough to use. There are rain gauges which are cheap enough that we could consider distributing them to every single school in Africa. Why not groundwater level monitoring equipment which could be used to keep track of groundwater levels in every community that has a community hand pump?
So my role right now is just to show you practically how these things work and a little bit about the background to each type of device. On the table here I've got this, which is actually known as a whistle or a plopper, because basically the way it works, which I'll demonstrate in a minute, but an electrical dip tape, which is the basic tool of any hydrogeologist, for those of you in the audience who are hydrogeologists. And then the third type of device, which is a pressure sensor, which is an automatic means of recording water levels. And so in this brief slot, I'll try and explain how each of these work, mainly with a view to those of you who want to have a go at designing these, the sort of features you need to sort of think about when you're putting one of these together. The plopper is a very, very simple mechanical device, and it's basically composed of two parts: a surveyor's tape, which you can buy relatively cheaply off the shelf, and a probe, a weighted probe on the end. And this particular device, this is a brass weight, and it's hollowed out. And the reason it's hollowed out is that when it hits the water level, it'll push air through the tube, and there's a little whistle at the top here, so it should make a little noise, which you should be able to hear as it goes down the well. This is a slightly sophisticated plopper, and it has these rings which are actually spaced exactly a centimetre apart, and therefore in theory I can drop this in the well, collect the water on one of these rings, and I know precisely where the water level is. Because one of the disadvantages of ploppers is you've got to wait, but you don't know precisely where the water level is, because you can't, unlike my borehole here, you can't actually see where the water level is normally down the borehole. Just like you to imagine that this is a borehole, this black mark represents ground level, and everything below here you can't see. So you can just ignore this. When you're reading a device, you're normally at the top of the well here, and you can't really see where the water level is. So just to demonstrate this particular device, I'm just going to get my partner here to hang on to it. These work simply by lowering into the well, and if you listen carefully, I hope you will hear the whistle as it drops in. Okay, so we know now we're at the water level, and if I can measure off here a reading, which is 0.44, and then if I just lower it a little bit, I'm cheating because I'm looking, and it's now reading 0.48, and if I lift this out, and then I can see that there's water collected on the rings to that level there, and then the zero mark on the tape is here, and what I have to do is actually fold this tape back and measure down to the top of that ring, which is 0.22, so it's 0.48 plus 0.22 is 0.7. Thank you, my mental arithmetic is very poor. 0.7 metres. So if you keep that in mind, somebody write it down for me, and we'll measure the water level in other ways. That's 0.7. So that needs a little bit of mental gymnastics with the datum point in order to get a reliable reading. The second type of device is the electrical dip tape. Now essentially the elements are the same as mechanical dip tape. I have a reel which holds the tape and a brake here to run. We have the tape and we have a probe at the end. The main difference here is we're using the electrical conductivity of water, or the electrical properties of water, in order to record when we hit a water level with the probe. So consequently, we have two wires running through this tape. And the tape, by the way, is graduated, this particular tape, in millimetre intervals, so it does allow you to read down to a millimetre level. You can buy cheaper tapes which are marked to centimetre intervals. And if you're designing one of these, there are various issues you have to think about in terms of materials and quality materials, particularly of the tape. But these two wires running down the tape are then connected to the probe. One connects to the outer casing of the probe, and the other to this stud running down the middle. And as you can see the insulating block in between, so that when we complete the circuit between those 2 points, it makes a noise. And in this case, a light also goes off. So that indicates quite precisely where the water level is. So to do a measurement in the well here, just allow the reel to run freely, and just measure down to the water level. We shouldn't really be looking, but here we go. There, and I've got a value of 0.69 metres. What did we get before, Richard?
47.
0.7. So it's a slight difference. This should be more accurate than the Plopper, but you can see the Plopper was within 1 centimetre, which is what it ought to be, and this should be within better than 1 centimetre accuracy. The other components of a dip tape are electronics. Now most dip tapes, the electronics to complete the circuit are usually buried away in the centre of the reel. In this case, I'll just take the centre off to demonstrate what we're looking at. These particular devices have got solid state electronics here. The cable from the wires are connected to these 2 studs, which then connect to the back of this bracket, and this whole unit is self-contained. And you also need a power supply. In this case, it's a PP9 battery, which just can slot in and out of there, and I can test the electronics on its own. You can design these much simpler, very much simpler, and that's a challenge. Can you design something simpler than this, which does the same job? Actually, I'll just leave that out for the moment, so you can see what's going on. So those 2 devices, I'll just flick through a couple of slides, is using it in a hand-dug well, measuring from, in this case, datum point on the side of the well. The datum point is a key issue, is where do you measure water levels from. And what you end up with these type of manual devices, as Richard was indicating, is we take specific measurements at a specific point in time. So you're taking a single measurement, and the frequency of measurements depends really on whether there's a dip tape available to someone on site and how frequently they can go out and measure it. More often than not, this is an example of a monitoring program where somebody is going out every 2 to 3 months and taking a dip measurement. And this is the sort of record you get of the change in water level. The third type of monitoring device is an automatic system involving the use of data loggers. Now there are a lot of different data loggers available on the market. I'm only showing you one specific type today. And this is probably the most commonly used for development work. It's what's known as a total pressure logger. And total pressure devices look something like this. These are just identical electronically, but they're just in different casings. These obviously can go down much narrower tubes than these, but essentially the elements of these are the same. And they measure water level changes by measuring the change in pressure acting on a sensor. And all these devices, a little hole here at the bottom of the device, that allows air and water to get into the bottom here, and the changing atmospheric pressure and the changing water level in the borehole will give a different response on the plate in there. There's a little titanium plate inside here. So the pressure will act on that plate, and that is then converted into electronic signal. And those of you electrical engineers will know far more about how that works than I do. And then inside there you have a circuit board, this mini circuit board squashed inside there, and a power supply. And these units are then totally sealed, and basically they will last 10 plus years if you look after them and in continuous operation. So how do you use them? At the end here is a connection point, and these can be programmed simply by plugging into a PC using a standard USB cable and some sort of docking device. So these would sit in there. I can plug this into the PC and program it. I don't have time to go through programming today, but you should hopefully understand the principle. Then having programmed this, you connect it to a cap, which I've mislaid, and these can be basically suspended with the cap into the borehole. The only other thing with total pressure devices is because you're measuring the total pressure on the sensor here, you have to do a compensation for change in atmospheric pressure. So if the atmospheric pressure is changing, and in the UK it can change by as much as 85 centimetres maximum air pressure, and we've been finding in Africa the changes are much less, but you need to be able to eliminate that change so that you can actually get a single water level measurement. So you will, with these, you will have a second device, sometimes located here in the top of the borehole, sometimes located somewhere else in the area that you're working. I just wanted to end this presentation just to show you what happens when you use a data logger. This is the log is already being pre-programmed. If I now turn it on, so you can actually see it, it's telling me to switch because it's a while since it was on. It's telling me the water level is 0.667 metres down, because I've already told it that. I've programmed it to tell it that. And it's taking a reading at the moment every 2 seconds. And if we look at all the readings collected, it's filling from the top, so you should see the water level, thankfully, is reasonably stable to the third decimal place, which is obviously 2 millimetres. And then we can actually show this as a graph. I'll just blow that up. What you're seeing there, because the water level currently is not moving, is the noise, the instrumentation noise. If you look at the scales, we're looking at the blue line is level, the black line is pressure. So probably best to concentrate on the blue line. We're looking at variations of about plus or minus a millimetre at the moment in the electronic accuracy of the equipment. So let's change the water level and see what happens. So just have a bit of rainfall directly into our borehole. Hopefully what you see is the black line is going up. That's because the pressure is increasing. And the blue line is going down because the depth to water level, which is the thing you're measuring, is reducing as I add water to the water column here. And I'll do one more. So you can see just how responsive this sort of equipment is as the water level is moving. Just expand the graphics so you can see the whole picture there. And of course, water levels go down as well as up, so let's reverse the process. Just use my little siphon up here to do that. You can now see the water level reversing and going the other way. I'll just leave that running. So the degree of sophistication is quite different between this and these. With these sort of devices, we can take readings as 2-second intervals if we want to. So we can take very, very frequent readings, and that gives us the ability to extract a lot more information about what is actually happening in a water body. Yep. Okay, so I hope you got the idea. That's a very, very brief introduction to data loggers. Let's just go back to the presentation. So this is what the setup in the field, because there's a borehole behind here, but as I say, you don't actually know what's going on down the borehole. This is a logger being programmed, this is a water level dictate. And it's worth saying that with automatic logging systems, you always need to do a check validation using an accurate means of measuring water levels. So you still need a dictate periodically to check your logger records. And this is the sort of data I was showing you earlier that you collected using a manual water level meter. Behind it is a record, the blue line, of a logger collecting data from the same site every 15 minutes over the same period. And you can see here the well was pretty much dry, it's the end of the dry season, and the rains came. And you can see we've got a lot more information here about the well than we get from single water level measurements alone. I think that's a good point for me to finish, other than to say what we don't want you to do is copy identically what you see in front of us here. The challenge really is twofold. Can you make a better one of these so that it's more practical to use? Better one of these or a better one of those? Or what I would really challenge you to think about is producing something which is quite different, but does the job efficiently, cost effectively, and reliably, and also accurately, I should say, as well. Okay, and that's a good point, I think, for me to end and hand over to Richard.
Great. Peter's anticipated some of the things that I would say, but in this second very short talk, I was asked to say something about the physical, the environmental and the human challenges that would be faced by a new design of a piece of equipment. I'm just going to very briefly make 10 points, 10 challenges. We need to be able to measure water levels, which are anything from, well, a few centimetres below ground to many tens or possibly even hundreds of metres below ground. If we're thinking about water supply wells in low-income countries, then typically those water levels would be most commonly no deeper than about 50 or 60 metres. But we need to be able to reach that kind of depth. We need to be able to measure within an accuracy of about a centimetre. Peter's suggested some of the accuracies associated with these pieces of equipment. With continuous recording devices, the data may only be downloaded every few months. As you saw in the data that Peter presented from Sierra Leone. So those automatic logging devices need sufficient memory and sufficient battery life to allow that to happen. In some cases, recording devices might be required to monitor water level every few seconds, for example, during a pumping test on a borehole. Whereas in more routine monitoring for water resources, we may be thinking about every 15 minutes, as in the data Peter showed us, or even every day, every week, or less frequently still. Peter's already mentioned that automatic measurements need that validation or calibration through manual measurements with something accurate and reliable like this. And again, in the data, you could see that those red data points fell exactly on the blue line, which represented the data from the logger. Practical challenges. I think again in one of Peter's slides, you could see that there was a pump hanging in the borehole. There may be pumps, pipe work, all sorts of stuff in the borehole, rather than a nice, clean, vertical, straight structure like this. So that kind of equipment can get tangled with anything that you put into the hole. Groundwater monitoring points, wells and boreholes for productive use, they can vary from 50 millimetres to 300 millimetres or much more. Hand-dug wells tend to be a little over 1 metre in diameter, at least in Africa. But never believe the pictures that you see of wells and boreholes in textbooks, which always show them as nice, straight, vertical, clean-sided structures. They are not. They can be non-vertical, non-straight, very jagged, if they're not lined. If a water point for domestic use is equipped with a hand pump, then almost certainly there will be no means of getting your equipment into the borehole. The hand pump sits over the borehole casing, over the top of here, and there is no access port to get the equipment in. There are some examples of monitoring programs in Africa where hand pumps have been modified by cutting a hole in the side of the plinth in order to enable access for a monitoring instrument like this. And that would be absolutely necessary. All field equipment, this is as good as new, I would say. See it after a month or 6 months or a year when it's been bouncing around in the back of a pickup. This sort of equipment gets abused and misused, and it needs to be really rugged. The context for the use of the technology, we're implicitly, I think, in this competition thinking about low-income countries, possibly remote rural areas where even access to simple things like batteries and other spare parts may be difficult. So that's part of the picture. And lastly, the users, the prospective users of the technology simply may not be familiar with using something like this, which we all struggled with when we first tried to use it. What exactly do you measure from where to where to allow for the fact that some of these areas of the instrument are full of water and some are not? Even these can cause problems when they slide down the inside of the casing. Maybe the probe hangs up somewhere and the cable continues to drop. They can cause challenges to the user, and a certain amount of training and familiarity is required, especially if the equipment's not intuitive. So these are just a few of the challenges. I'll leave it at that. I'm going to hand over to Geraint to say a little bit about finally about the structure of the competition, and then we'll take the questions and any comments that you might have. Thanks.
The winner of the competition will be provided with a £1,000 cash prize, and will also have the opportunity to work with Creative Design to take their idea and turn it into a working prototype with the idea to test its suitability for manufacture. Everything that I'm about to talk to you about is in the competition brief, which can be found on the Engineering for Change website, and I'll provide a link to that in a second, so you can download it all on the competition brief. So we've broken the competition into two categories, based basically on existing technology. The first category is an improved low-cost mechanical or electrical dip meter, i.e. a device that requires human input to take a measurement. And the second category is an improved low-cost automatic logging device, i.e. a device which doesn't require human input to take a measurement, can do that automatically, storing the data until somebody comes along to collect it, or perhaps transmitting it to a computer or a mobile phone or something like that. Now it might be that your technology, your idea, fits into both those categories, and that's absolutely fine. It would be judged under both those categories. Might be that your idea is so far out there that it doesn't even belong to either of those categories. If that's the case, that's fine as well, and as long as it's trying to solve the real-world problem that we've tried to outline, then it will be judged accordingly. As in, it will be viable. So, who can apply? This competition is open to anyone, anywhere in the world. Group entrants are welcome, as well as individual entrants. The only stipulation we apply is that the maximum group size should be 6. Key dates to put into your diary. The first is the end of this month, so November the 30th. That's the date that you need to register by. Now to register, it's just simply going to the Engineering for Change website. There's a link there, but that link can also be found on the Engineers Without Borders website, UK website, and the Hydrogeologists Without Borders UK website. So you can go to just Google search that, and then you can find that link. So go to that website, download the registration form, fill it out. It will take you about 5 minutes. It's just asking for contact details, and then send it to the email address provided on the form. And that's you registered. The second key date is January the 31st next year, 2014. Now it's at this point when you need to put your idea, your concept, onto paper and then submit it just for the judge's eyes only. This can be submitted we're suggesting a format of either an A3 sort of poster or a couple of sides of A4. We're not looking for massive detail, we're just looking for you to sort of give us your overall concept, that idea. And this is a great opportunity for you to then get feedback from all the judges who will perhaps provide some tips on whether, where the challenges that your particular technology might face, give some suggestions, or if the idea doesn't appear to be meeting the competition brief, then that would be, again, the opportunity for the judges to say, look, I don't know if this is going to work according to what we're looking for. Why not try and consider something else instead before that final deadline of May the 1st? So the final date is the May the 1st, and that's, you need to have submitted your submission, your bid for the competition needs to be placed in before the 1st of May. We're not being prescriptive as to how you submit. You can submit detailed design drawings, you could submit video, photos, or a working model. It's up to you. But remember, you need to persuade the judges that A, your idea is going to work, and B, it's worth taking on to prototype. So the more detail you can provide within that submission, the better. as a way of an example, if we were to take, let's say the dip meter hasn't been invented yet, and you had the idea of the dip meter. So you could submit a design drawing showing that dip meter in drawings, or you could submit a design drawing as well as perhaps a video of you with a couple of electrodes, plonking them into some water, creating a connection, and there's a buzzing noise at the top. And by demonstrating the concept behind the drawing, I think that would be much more persuasive for the judges. So we have got some judging criteria, which is on the competition brief. I'm not going to go through that now. Richard and Peter have already gone through it. The only thing I would mention is that one of the main challenges with current monitoring equipment is the price. And so it would be good if you could submit within your bid a cost estimate of manufacture of the products, which would put into that design. So that would be useful if you could do that within your bid. Prizes: each category winner will receive £500 cash prize, and then the overall competition winner will receive an additional £500 and the opportunity to work with Creative Design to take their idea forward to prototype. And I've put here that the designer will have the opportunity, or designers will have the opportunity to work with Creative Design with as much or as little involvement as they wish throughout this process, gaining invaluable experience in product design. This really is a fantastic opportunity for an individual or a group of individuals to turn an idea into a reality and gain some invaluable experience with an award-winning product design company, and perhaps, if the idea is good enough, revolutionise the way that groundwater level data is collected. There will be additional prizes of £500 for runners-up as well. So there's only a couple more points. Everything that is submitted into this competition will be under a Creative Commons Attribution Share Alike license, which basically means that your work will be attributed to you, but it will be free for others to use, share, or adapt. And I would like to take this opportunity to also thank the competition sponsors who are making this all possible: Peter Dunbar Hydrogeology, Creative Design, and SKM. So now we're at the question and answer session. Oh, and can we also thank Peter and Richard for coming along today?
You mentioned the kind of options of, I guess there are different price options, option 1 and 2, is what's kind of governs them. How about depth options? Is that realistic that you would have something that measures in centimetres if your level is something that you know hovers around 10 metres all the time, or less than that, or something that measures within tens of centimetres if the kind of depth you're talking about is 40 or 50 metres?
Ideally, we'd like something which can measure accurately at the maximum depth that the instrument can operate. I think what you might need to choose, not knowing where you're going in design terms there, but choose is if your design may have limitations itself as to how deep it will work. And so you need to make a judgment. As Richard said, ideally it needs to be within 50 to 60 metres would be a typical depth for most applications, though there are many wells which are much deeper than that. Dip tapes inherently are governed by the length of the tape. Standard dip tapes range from 30 metres upwards. That particular one I think is 50 metres. So you have to think about the length if you're using the manual method as to where it will work. If it's automatic, it's governed by the head water acting on the sensor. So it's a long way round of answering your question, but it needs to be reasonably consistent whatever depth you are at. One last thing on accuracy with tapes, the longer they are, the less accurate they are because they stretch. The longer they are, the more they stretch, and it's a sort of, those of you engineers will know that because you've got a weight on a material, and the stretch depends on how on the material that it's made from. These particular tapes are all reinforced, for example, with either stainless steel wires, or this particular one has got Kevlar sleeving all the way through it, and that prevents it or reduces the stretch with length. So therefore, the deeper these go, the less accurate they will be. But it's a linear accuracy change.
I suppose just one other point is that both these types of equipment are very accurate as they stand, but they're quite costly. So there is a gap in regards to less accurate equipment, but at a much cheaper price.
I think it's worth pointing out as well that whatever you come up with is going to have constraints. That dip tape, if it is a 50-metre tape, you can't really use it beyond 50 metres. So there are automatic built-in constraints, and logging devices have certain ranges over which you can use them. So that's fine. I mean, that's assumed.
Out of interest, how much do these take?
Well, relatively speaking, these specific ones, the plopping device, I mean, it's a surveyor's tape, and then most of the cost, the manufacturing cost, is in the weight, and it just depends who does it and for how much. But that as a commercial tool would cost between, say, £75 and £100 to buy in the UK. The dip tapes, well, that particular one is over £300, that's probably 350 plus. But you can buy much cheaper dip tapes starting from around 150 to £200. But you basically buy what you get. A lot of the quality is in the tape design with dip tapes. Logging devices, this particular one is under £300, about £280. But don't forget, you also need a reader and so on to get started. To get started with logging, you're usually spending between £700 and £1,000 for initial setup, and then £300 a logger beyond that. But you can actually spend an awful lot more with loggers than that. You can get into thousands of pounds if you want to go at market with logging devices. So it gives you a broad range, I hope.
You mentioned at the beginning that ideally we'd be able to have some measuring implement in every community with a hand pump at the end of the day. So what kind of cost for a cheaper logger would you need to have? How cheap would it need to be to distribute them kind of that widely?
I made the comparison with cheap plastic rain gauges, which are still quite accurate, but they don't measure up to the specifications of a standard sort of sharp-edged meteorological rain gauge. They cost about $30. If they're manufactured in developing countries, even that figure could be brought down a bit. So I'd say something of the same order. If we were to have, I mean, so many communities in Africa and Asia have at least one borehole or well from which they get their domestic water. If we could monitor even 10% of them, that would be fantastic. We probably monitor, well, we don't monitor any at the moment. There are a few African countries that have groundwater monitoring programs. Uganda, for example, I think there are 10 stations in the network for a whole country of 30 million people.
Can I just mention as well, one of the features of a lot of Africa is mobile phone coverage can be very, very good. And the potential to use of smartphones, they're already being used in quite clever ways for different aspects of development work. It maybe there's something there that you could use an app linked to a device in some way, which sort of is a hybrid then of the logging facility and the manual facility. Certainly worth thinking about.
There's a lot of dialogue and correspondence been going on about mobile phone-based technologies for monitoring of water supply services in Africa. If you look on the Rural Water Supply Network, RWSN website, you'll be able to track some of that. But none of it deals with the issue of monitoring of the resource. It's all about is the hand pump working, and if not, what needs to be done to fix it. And it's about coverage levels, different geographical areas, how many people are served, what percentage of the people are served. But there's nothing about water resources. So I think Peter's point is a good one. To link into some of that debate would be interesting.
Just one other thing about cost. $30 would be amazing, but as Peter mentioned, it's £1,000 to set up a logging device, and that really is off-putting people from investing in any kind of technology within a project, because that's a lot of money that could be nicked. If you drop it even to half that, we're really onto something.
Just have a question on the kind of value of the data, I suppose. When you say you collect this groundwater level, but you can't tell what's natural and what's from the users, is that what it would eventually be expanded to in an ideal world? I'm just wondering about the value of this data when you don't know how much water is actually leaving via the pump and what's the natural fluctuation.
Yeah, it's a very interesting question, and it's one we've been grappling with in a program that Peter and I are doing in Sierra Leone. The groundwater level data on its own is probably of limited value, although it can. Sometimes you can get surprising amounts of information out of just the groundwater monitoring data. Even the data that Peter showed there of the Oyo Memorial School in Bombuna, those fluctuations on the blue line that you saw, we could certainly hypothesize with some degree of certainty as to what was causing them. And where levels were dropping to the base of the well, that's almost certainly to do with dry season abstractions, and then recovery overnight, and then drawing down again in the daytime. Whereas the fairly steady upward trend in the rainy season has obvious links to the groundwater recharge process. But what would be ideal is to be also monitoring rainfall near to the place where you're monitoring groundwater levels, and monitoring abstractions from the well, if it's a productive well in use rather than purely a monitoring well. And then over the longer term, looking at any changes in weather and in land use, because those will affect the amount of recharge. Now that's not part of this competition to take it that broad, but to answer your question, really we need that scope of information in order to make full sense of the groundwater data.
I could just add one used thing from the wash point of view is gathering data at 15-minute intervals. You can actually map the social activity at the well. Certainly we saw in some of the wells, 4 o'clock in the morning, the first person would be out there taking water, activity increasing around about 6 o'clock and so on, and you could actually see how frequently and how intensively the well is being used and actually draw other information from that. And I think Richard had as he monitored a well at 1 minute intervals for a 24-hour period, you can virtually see every bucket of water that has been taken out of the well when you
extrapolate as to what the total extraction is. So there's a lot you can do with the data if you make assumptions.
How narrow would a well be, or how narrow would you advise it to be?
just jumping to the design brief suggests a diameter for the probes on the end of these devices or the logger itself. You can see they tend to be fairly narrow, and narrow in general is an advantage. The smaller diameter you can make these things better. I think for practical purposes we've said 25 millimetre diameter. I can't remember.
50, yeah, 50 millimeters.
50?
Yeah, 50, 50.
50.
Is that correct?
That's quite big. But the logger there is about 25 mils, that's about an inch. These devices are less than an inch. So you need to think in that sort of range for probes. I know Richard always wants to get things down incredibly narrow access tubes, so the smaller the better in terms of diameter. But don't be put off if you can't get to very small diameters. We'd rather see some interesting technology coming out of this, or some good ideas. But diameter is pretty critical in some instances. But in fact,
Although, I mean, just to add to that a little bit, if you've got a productive borehole which is delivering domestic water, or even more than domestic water, maybe irrigation water, the casing for the borehole will have a minimum diameter of 100 millimetres. So if you're planning to put the measurement device inside the borehole, and you're not expecting too much in the way of obstructions from pumps and pipes, then it could be quite large. But sometimes these boreholes have monitoring tubes down the outside of the casing, which are quite small diameter, and that's the origin of Peter's comment there, where in one particular case in Ethiopia, I was looking for loggers which would go inside 25 millimetre pipe, and this was too big. The slimmer one would have gone, but this is more expensive than that. So again, it's horses for courses, and there will be constraints.
But the only way to get into a solid hand pump is to drill a hole in it if you want access to
Yes,
it.
I meant to actually put up a picture of that, but the hand pump, if you imagine again, this is ground level with the borehole casing sticking up. The hand pump pedestal sits over this casing, and it's a steel tube. And what you have to do is cut a window into that, so that the monitoring device can go down inside the borehole casing, between the casing and the rising main from the pump, which is quite a small gap.
Or you have to dismantle the pump.
Yeah, but realistically, doing that every time you want to take a single measurement is not realistic.
But if you had something you might leave in there, it could be possible.
Yes, but bear in mind that even with an automatic logging device which you might leave in the hole, you do need to go back at intervals, maybe only every 2 or 3 months, but to take a manual measurement. So you need access. But this is a constraint of the pump, and it shouldn't really affect you in terms of your design of the monitoring instrument. It's more background awareness. But it does show the kind of disconnect between people who are in the business of supply of water, as opposed to those who are more concerned with the resources. to design a hand pump, all hand pumps, in such a way that they do not allow access to monitor the groundwater resources is very short-sighted, and yet that's how all hand pumps are.
Any more questions? Great. Well, thank you very much for coming, and you can ask your questions as well. If you have questions.
Good luck.
Yeah.
A bit of applause for you.